Okay, so I guess short story long. Back to what a GPU is, we think about this guy as, again, being a collection of magic tricks, but it's domain specific for solving kind of floating point problems. Now, Van over here, he holds the record here for the most cores on a single CPU, right? You got that 36 core CPU, so, it's, okay, so, yeah, so I mean, that's awesome, situationally awesome, I guess, but, how many cores do you think are in a GPU?
More than 36 or 4.
Think 2 or 4 cores in a GPU? GPU. See these guys.
More.
So you think it's 2 or 4? What do you think? Any guesses? So he's got 2 or 4 cores in a GPU. What do you think? Whoever, this is like prices. Is it Price is Right, or is it Let's Make a Deal? Or you get to choose the price. Can't go over.
Price is Right.
Price is Right. How many cores in a GPU? 19?
Multiple.
Many cores. Well, how many? That's not a number. I need a number.
That's not wrong.
30? 32. 32 cores. What do you think? $36 cores. Shika? 30, oh, so you're just stealing her answer.
No.
Did you say 36?
Yes, but
That's the answer she just gave,
okay.
So
I think more than 36.
So you think 37.
Yeah, more than 36.
What about Edwin? What do you think?
I think it's more than the CPU, like 1,000 cores, more than that.
You got it.
This process, the video is going to be faster.
How many you think?
Not 8 to
8 to 12? All right, so a modern day pretty good GPU, let's like a GTX 1080 or something like that, has over 2,000 cores.
Yeah. Because process the video is not like process the multitask like CPU.
So think about the space it takes. So when we have one of these general purpose CPUs, maybe they're that big or something like that. All right, those general purpose CPUs, they have 4 cores in them, let's say, or 6 cores, and they have thousands of transistors, but they also have a bunch of magic tricks, right? A whole bunch of magic tricks that they can do to solve those problems. We mentioned that GPUs are domain specific. They have far, far, far fewer magic tricks. All right, so with that in mind, you could fit more cores into the same space because you have room because you didn't have as many magic tricks. Make sense? So numbers you'll see is like 2048 for number of cores, that kind of stuff, in some of the high-end GPUs. And as new ones come out, they typically have more cores or more RAM, that kind of stuff. They typically don't necessarily advertise number of cores on GPUs anymore. The assumption is just it's a lot of cores, in the thousands for a number of cores. So really the thing that differentiates the GPUs is typically RAM, how many gigabytes of RAM. So 11 or 12 gigabytes is on your high-end graphics cards. So a GTX 1080 Ti has 11 gigabytes. A Titan X has 12 and a lot more expensive. Most of our modern higher-end graphics cards have 8 gigabytes of RAM. That goes down to like 3 and 4 for your borderline lower end ones. Okay, so in any case, a GPU is like a CPU, except it's more general or more domain specific, and you get a lot more cores because it's only doing math. Lots and lots and lots and lots of math. Okay. So we talked about types of computer systems in terms of PCs and servers. Now, what about embedded systems? You mentioned earlier that a graphics card is a computer, right? So would that be an example of an embedded system? So kind of a computer embedded in something larger? Does a car have an embedded system in it?
Yeah.
No, a car isn't all a computer, but there's probably multiple computers inside of a car. right? So that's an embedded system. So when you are thinking about the architecture, whether you're programming an embedded system or you're thinking about the resources for an embedded system, those things scale based on what that system has to do, right? So when we talk about smart fridges, like we talked about Internet of Things earlier, a little bit the IoT stuff, which is, the idea that your fridge has to have an internet connection. There could be an embedded computer in that fridge that keeps track of like when you're running low on milk and stuff like that. Does that really need to be a very powerful machine? What about Fitbits? Is that an embedded? Is that a computer system? An embedded computer system? You wear the little wristband thing that's counting your steps. So it's only doing a couple of things, right? It's kind of counting your steps and does something with accelerometers and maybe something with GPS. Now they're getting a little bit more advanced where they'll play music or something like that. But generally speaking, does only some very specific tasks, right? So going to have a processor in it, but probably not a really, really, really fancy general purpose processor. It's going to be something that can handle what that device is supposed to do. All right, so punchline is that there's a whole bunch of different types of computer systems. Fair enough? All right. Now, a little bit ago, we were talking about the amount of RAM on a graphics card. So let's do sizes of memory / storage. So how much RAM is commonly in a desktop computer, a PC? 4 gigabytes, 8 gigabytes, 16 gigabytes. How much RAM is in yours, Van? You have 128 gigs of RAM? Jeez. It's a beast. Just a beast.
This is just a computer only, not the cooling system.
He didn't wrap the cooling system into the 10 grand price tag.
The cooling system is more than 10 grand. Just the graphic card only about, free graphic card cooling is about almost 1K.
Right. Well, then your graphics cards, each of your graphics cards are like $700 graphics cards.
Yeah.
So you have $2,100 in graphics cards.
Yeah, but not the cooling plates. So you have to order the cooling plates.
Right. So you got $3,100 in graphics cards plus cooling. Then you got another $2K for your CPU. They're at 5. And then you got your 128 gigs of RAM. All right. So most PCs. So we think PCs. We're probably talking 8 or 16 gigabytes of RAM, right? Something like that. All right, graphics cards we mentioned earlier, so we'll just call it GPUs to keep it shorter, which actually that's the processor, not the card itself. But graphics card maybe has, on average, probably 6 to 8 gigabytes for a decent graphics card. The higher end ones have more, but you're starting to spend quite a bit of money for that. They get up to maybe 11 or 12 gigabytes, but you're talking an expensive graphics card at that point, like close to $1,000 just for the graphics card. Okay. What about jump drives? We get USB sticks, jump drives. What's the size of those?
32.
So 32 gigabytes, 64, 128. What about hard drives? 1 TB, 2 TB, 3, 4 TB. It's pretty big, right? What about SSDs, solid state drives?
Lowest one is 128.
So 128 gigabytes. 1 TB, but you're starting to get pretty pricey at 1 TB, right? Okay.
I don't use SSD.
But still SSD.
Oh.
Yeah, it's still a flash-based thing. It's just the connection is a different connection. So it's not a serial ATA connection. It's an M2 connection.
Yeah. It's faster than SSD.
It is. Well, it's faster than serial ATA. It's still a flash-based memory. It's still the same kind of technology that's an SSD. Just your interface to your motherboard is different. It doesn't hook in through a serial ATA cable. It hooks in through an M.2 cable or an M.2 port. It just plugs right in.
Yeah, that's why my computer doesn't have a lot of wires.
You don't have room for a lot of wires.
Well, it's have a lot of room for wire, but I don't have any wire beside the core of motherboard.
So is your 128 gigs of RAM, is that a bunch of 8 gigabyte sticks? Or is that a whole bunch of 4 gigabyte sticks? 4?
No, it's not 4. It's 16 per RAM.
So you have a bunch of 16 gigabyte sticks?
Yeah.
I didn't even know that they were out yet. Expensive RAM. We should have a demo day in the cafeteria sometime. Just have you bring your machine in.
It's super heavy.
I know you brought it in for the VR thing for the hackathon.
That one, it's just halfway.
Oh, it's not done. It wasn't done yet.
The one that I bring here, it's just half pound, halfway. Just like now, I think it's 30 pounds on that. But this one is more than 30 pounds, more than 60 pounds.
Yeah.
When I carry it on the table, I couldn't carry it myself.
That's ridiculous.
I want to build the computer, that it's completely underwater. I already have plane. You can use a mineral oil.
Yeah, right. Yeah.
To build the computer component, everything is under the mineral oil. But I don't want to dip my money into the oil.
Literally.
And it burn out someday. I don't
Yeah, you
know.
got to use an inert fluid that doesn't conduct.
Yeah.
Man, I can't decide whether I'm impressed or sickened.
Well, I already built one small one for my mom. It's underwater. It's have a fish go around.
So you have a computer that you built for her that has a fish in it?
Yeah.
We need a video of that.
Okay.
that's
But the cheap motherboard, cheap graphic card. So basically, you don't use much of the computer. But it's like
What is it? A fish tank?
Yeah, the fish tank you can buy in the glass, and then you can buy silicone just like go over it, and then you can put one side of the fish, one side of the computer.
What kind of fish?
Goldfish.
Goldfish. Well, that's gonna die.
No, it's split up with the water and the mineral oil.
Well, don't goldfish have like a life expectancy of like a month?
What do you mean?
Like how long do they live? Goldfish.
I don't know. It still lasts for now.
How long is it? She had it?
It's like a couple of months.
Yeah, so we're getting the end is nigh. All right, so SSD, a little bit smaller. What other kind of? What about? Have you heard of things like cache memory? So cache memory. Well, let's just say what are sizes we might have for cache memory? L1, L2, L3 cache. Maybe 1 megabyte. 4 megabytes. Something like that. Small, relatively speaking. All right. What about registers? Hardware registers. Really, really small. So this might be 8 bits. Well, let's just go 1 byte, 2 bytes, 4 bytes, so on and so forth. So then the question is what does all this stuff mean? We throw around these terms. And what's pretty common for technology people is we get so used to saying like, oh, I have 16 gigs of RAM, or I have a 2 terabyte hard drive, or I have a 512 gigabyte solid state drive. I have 4 megabytes of L2 cache. Things like that. Do we actually know what those things mean? What's a bit? What's a single bit? 0 or a 1? Now, why do we have bits? Why are computers implemented in terms of bits? On or off, digital logic, right? On or off, 0 or 1. Okay, what's a byte? 8 of those bits. Okay, what's a kilobit? Low B, bit. Of what? Bits. Okay, so this is 1,024 bits, right? Now, let me pause for a second. How many of you have internet at home? What's the speed of your connection?
120
120 what?
megabit.
Megabit? So you think it's 120
Yeah.
like that?
Yeah.
What's other people's? 100? Okay. Megabit per second? What's yours? 48? It's a weird number.
Probably even.
It's possible. It's possible it's 48, but so 48 megabits per second. Now, Van answered first because he's already heard this this thing from me before. Typically, technology students don't get the answer right quickly initially.
Yes.
What do they say? They have, oh, I have 120 meg internet. 120 meg internet. And typically when they're saying that, they're talking about megabytes. Okay? So first of all, most people who say how fast their internet is, they don't even know what that necessarily means. What is 120 megabytes versus megabits? To them, it doesn't matter. You can measure their internet speed in terms of nachos. Okay? But typically they just throw out their megs of 120 meg internet. It's like, oh, well, how fast can you download stuff? Fast. Download it fast. I got 120 megs. So then the question is how fast is this really? And to understand that, we have to have a concept of size. So you said that a kilobit is 1,024 bits. How big is a megabit? 1,024 kilobits. How big is a gigabit? 1,024 megabits. How big is a terabit? Which is nobody uses that phrase yet, but soon it will be. So that's 1,024 gigabits. How big is a kilobyte? 1,024 bytes. Megabyte is 1,024 kilobytes. Gigabyte is 1,024 megabytes. Terabyte is 1,024 gigabytes. So when somebody says they have a 2 terabyte hard drive, they actually have 2 times 1,024, so that's a 2,048 gigabyte hard drive. Times 1,024, it's actually a 2,097,152 megabyte hard drive. Now, in the early days, when hard drives started getting bigger and bigger, Best Buy used to advertise them in terms of the number of bits. Because the bigger number means bigger, right? People go in, they go, well, a trillion bit hard drive, just had a whole bunch of zeros in it. And the same thing happens to consumers today with internet. So Van here says he has 120 megabit per second internet connection. How many megabytes per second is that? divided by 8. So 120 divided by 8. So his theoretical maximum internet speed is 15 megabytes per second. That make sense? So if you were buying internet from, so he's got cable internet, right? So how do I know he has cable internet and not DSL? Anybody in here have DSL? Anybody know the difference between DSL and cable? It's an embarrassment.
DSL is,
DSL is from the phone company.
yeah, phone company.
So AT&T would sell you DSL. And the fastest you can get with DSL, it's like 24 megabit per second. But you got to be lucky to get that. Typically, you're going to get 12 to 15 megabits per second maximum speed on DSL. Because it's very related to how far away from the, what's called the DSLAM, how far away you are.
AT&T, they claim they have 15 to 16 megabits per second. Right?
Not for DSL, they don't.
It's DSL.
No way. Show it to me.
I don't know.
Yeah.
Like last time, Mark.
Well, AT&T does have gigabit internet in downtown Milwaukee, actually. So if I lived in downtown Milwaukee, I would have gigabit internet. But it's not DSL based. It's a fiber. It's a new technology. It's a fiber to the house based internet.
Oh,
All right. So, and think about that. So possibly, and Google has this in some cities. Some people have gigabit, 1 gigabit per second internet, right? Which is equal to 1,024 megabit per second, which is equal to 128 megabyte per second. So if you're buying internet, which looks faster to the average consumer, 120 or 15? 120 looks bigger. So when you watch the commercials, notice they write megabit per second on there, but they say meg. Like you can get 120 meg internet for only $19.95 or whatever it is, because they're trying to sell you on the larger number. When actually the amount you are getting is still fast. 15 megabytes per second is good for today. So I do luck out here. I do have faster internet than Van. So I have 300 megabit per second in my house.
That's why long time ago when I didn't see this and you're talking before, this is why when I download with IAD Internet Download Manager, I only got like 10 megabit download per second.
Yeah. Okay.
My internet is 120.
Okay. So let's talk about that. Okay. So why do you need faster speeds?
Make the work done.
What do we use our internet for today?
No.
Do we just use it for email, things like that?
No.
How many of you watch Netflix or some streaming stuff? Does that take up a lot of network stuff? How many of you play online games? Take up some network stuff?
Yep.
Okay. How many of you maybe download some files? Certainly not illegal movies, but something, maybe Christian hymns or something. Highly compressed hymns. All right, so our internet has very much become a resource that we're using for many different things in the home. Especially now we start thinking about Internet of Things, where our fridge is using a little internet connection, our toasters are using an internet connection, our cell phones are using a bunch of internet connections when they're checking email and things like that, sending you push notifications, whatever. So that resource that we have in our house is being pulled on by a whole bunch of different sources, right? A whole bunch of things in the house are using our total bandwidth. So the reason why you might need a higher bandwidth, a higher total bandwidth, has less to do about what your performance will be from a single source. Netflix is only going to push you data at so fast, right? So Netflix has a tier where you can get 4K streaming, for example. And so you need to have, I think, a minimum, I think they say 60 megabit per second internet connection in order to get that. But, the point is 60 megabits per second isn't enough to get 4K. And we're going to talk about that here in a little bit. They're doing all sorts of compression stuff and things like that, kind of proprietary stuff. But the point is that even at 60 megabits per second being the requirement, you're not going to use all 60 of your megabits per second in order to get your 4K Netflix. Maybe you're going to use 15 or 20. Okay, so why do you need more megabits per second? The more people who are doing things using the internet in your house, or the more devices that are doing things using the internet in your house, the more total bandwidth you need, because they each are taking a little. Very, very, very few sources, as Van kind of just pointed out, will push you 15 megabytes per second, right? So when you do a speed test, the speed test used to be fairly accurate when people's internet was kind of far slower than the servers they were testing against. Well, if you have a gigabit internet connection now and you could pull 128 megabytes per second, it's possible that the server that your speed test is hitting isn't giving you it at 128 megabytes per second. You'll take it all day long, but it's not serving it to you that quickly, so you're going to get a bad read on what your speed of your internet is. That make sense? If you're really, really thirsty and they force you to drink out of one of those little cocktail drink straws, you only get so much so much water in at a time, right? Where you kind of just want, you want the big straw, you just chug the thing. So this is kind of an area where I think consumerism gets to you, where they're selling you on different speeds and things like that, and you rarely are going to find technologies that will allow you to truly maximize your internet speed at your house from one source. It's typically how much your internet gets divided across multiple sources. Make sense? All right. So that's more of an internet discussion, which more of a networking type class thing. Not really that important for us specifically, but the idea of the sizes, the megabits versus the megabytes versus the gigabits, those are things that are important to us because we're going to be thinking about how data moves around a computer system a lot. All right. And we want to have a concept of what's big, what's small, what's very small, so we can really think about the amount of data that's having to move around. All right, so we're going to spend some time today kind of talking about that stuff. All right, so this is something that all of you should know. If you don't have this memorized, I would memorize this. I mean, whether I quiz you on it or not is insignificant, but every single computer scientist should know this. Okay, and if you notice pretty quickly, it's a pretty easy pattern, right? Okay, but we want to know, first of all, you want to know the order, that a megabit is bigger than a kilobit, gigabit is bigger than megabit, megabyte is larger than bit, things like that. And you want to know how they scale and how you get from one column to the other, being a multiple of 8. Make sense? All right, so we kind of already talked about this data speed thing. So I'll just, here, let me do this. I'm just going to put that after data speed. Okay, so I'm going to go ahead and pop open the book here to 1.2. All right, so some of these things we already talked about, but each of these are going to kind of turn into a short discussion, just kind of introducing some of the bigger concepts we're going to get into. Earlier we maybe didn't mention it by name, although I think you maybe said the name, Moore's Law. This idea that integrated circuit resources double every 18 to 24 months. So I'm not sure that's entirely true anymore, but things are still getting faster. Computers got really fast really quickly, and it certainly has slowed down. And now what have we done? We've started looking at introducing more individual cores rather than faster individual cores, things like that. So we've changed the way we've approached it a little bit, but whatever. We certainly are looking at how do we make tomorrow's technology better than today's technology, whether that means speed, whether that means more resources, making it smaller. That's kind of our trend right now, right? Our phones kept getting smaller and smaller and smaller, and now our screens kept getting bigger and bigger and bigger. So we're kind of bouncing back a little bit. How can we have this thing be a fully functional computer yet having a screen basically the size of a TV set? I had this really cool device. It was like $12. It cost nothing. I would highly recommend it. I'll give you a link to it later on or something. But it's like this flexible metal thing that goes around your neck, and on the end of it, it has like a little holder for a cell phone. And you can put the cell phone on it, and you can bend this thing however you want. Okay, so I was using it on the airplane. I was using it on our cruise we were on. So you could put your phone like right there, so you don't have to touch it. You're just sitting there chilling, and you basically have a big screen TV, depending on how close you put this to your eyes, right? It's like the greatest thing ever. And I would sit there for hours and watching these shows and things like that. So, these guys have become entertainment devices. Now, I binged watched the entire series Grimm when I was on a 2-week cruise on this device. With no hands. Just sat there watching it. But now we have this situation where we're trying to have maximum battery life, maximum performance, maximum screen size. We still want it to be lightweight and slim and all these other things. But it has to be good speakers. We want everything, right? We want all sides of that. All right. So, Moore's Law has kind of taken a little bit of a different twist, but we still have a goal of making our stuff better. And we can probably say that our stuff is getting twice as good every 18 to 24 months. And that's probably a relatively fair statement. Make sense? We're not really measuring it on the number of transistors that are there. We won't be measuring it on kind of more overall perception or end user usage, that kind of stuff. But so next thing, abstraction and simplified design. Both computer architects and programmers had to invent techniques to make themselves more productive, for otherwise design time would lengthen as dramatically as resources grew by Moore's Law. Major productivity technique for hardware and software is to use abstraction to characterize the design at different levels of representation. Lower level details are hidden to offer a simpler model at higher levels. So let's think about abstraction. So abstraction is a synonym for simplification, right? It means simplify things. Human beings, we like to design things kind of at a high level. And then once we kind of have this large 2,000-foot view kind of concept of it, we then drop down and we start thinking about the details, right? Explode it out into the individual details. But still, at the end of the day, a human being wants to work with a certain abstract level of something. We only can function at such a level of detail. Zeros and ones really aren't our cup of tea, even though computers like those. And we'll talk more about that in a little bit. Okay, so something we usually think about with computing performance is make the common case fast. Okay, we kind of alluded to that earlier when we were talking about how one of the new magic tricks that might get introduced on a processor might take 3 existing magic tricks, combine them together because they're often used, and give you that one case, which is a common case, and make it really fast. Okay, so that's one of our goals. If there's something that is used disproportionately more than other magic tricks, let's see if we can make that guy faster, because now you have the average user is going to gain more out of that chip, even from just a little bit of an improvement overall for the chip, but a big improvement for that one task. All right. So we already had this discussion today. Is performance versus parallelism. Is it better to be fast, or is it better to have an army? Okay, it depends if we're changing a light bulb or raking leaves. Make sense? All right. This other thing, performance versus pipelining. We'll talk more about this later, but this actually has more to do with how instructions are fed to a CPU. So we have some strategies for making sure that a CPU can get an instruction, whatever that means. We'll talk about that stuff more quickly. And it's something you kind of asked earlier, I think, where even if you have 2 cores and 2 things can technically happen at once, doesn't necessarily mean we will have 2 things happening at once if one of those things is reliant on the other thing finishing. Make sense? And at the same time, keep in mind that even in multitasking, even in problems that can be divided, more often than not, you do not get twice the performance out of 2 cores. You get maybe 1.8 times the performance, because there is overhead for having to schedule for those 2 separate cores, having to ask some of those questions like, can this guy and this guy both happen at the same time? Or is this guy reliant on this guy? Does that make sense? So it's a harder problem to solve when we're having to schedule tasks for more than one CPU, when certain tasks might be reliant on other tasks. All right. Performance versus prediction. So this is something we really haven't alluded to yet, but sometimes when we're talking about computing stuff, we have to think about guessing. Sometimes whether it's the operating system or it's the hardware itself, we might have to make a judgment as to whether something will likely occur. And if it will likely occur and we can predict that ahead of time, then we can actually make the system quicker. But if it ends up not occurring, then it's going to take us even more time to back off and undo what we did. Does that make sense? Okay, so sometimes we need to think about things like that. We've talked a little bit about this already, kind of the nature of different memory sizes, and we're going to be talking about that over the next couple of minutes as we look at that conversion stuff, some of this conversion stuff. Our hard drives are larger than our solid state drives, which are larger than our system memory, which is larger than the various cache memories, and so on and so forth, right? Okay, so different kinds of memories, and typically the larger the memory, the slower it is. Smaller the memory, faster it is. All right, and more expensive per bit or byte, however you want to measure it. Dependability versus redundancy. A lot of times this comes down, we see this in hardware. We kind of talked earlier about an example that's kind of related to this with the Quadro graphics cards, how they're significantly more expensive, but they only really benefit you on a very specific cases. Similarly, power supplies. Okay, so let's take a guess. Vans, do you have I want to say you have a kilowatt power supply, but it's probably bigger.
1,500.
You have 1.5 kilowatt power supply. Okay, so he has a 1.5 kilowatt power supply. Now, actually, and you just have one power supply?
One.
Okay, so then he has a consumer grade power supply, a 1.5 kilowatt. It's a nice power supply. But there are server grade power supplies that are substantially more expensive. They typically don't come in 1.5 kilobytes or kilowatts rather. They're usually 850 watt or something like that, but then they're linkable, so you can have multiples connected together. But they're a lot more expensive. So somebody might say, well, why should I pay $250 for an 850 watt power supply? Well, I can get the same power supply for $70. Well, they're not necessarily created equal. When you have a server class power supply, that's making some assumptions, right? That machine's probably going to be on 24 hours a day. It's going to have to be able to deal with little fluctuations in energy, brownouts, things like that. It needs to work. Whereas your 850 watt power supply that you can get for 60 or $70, it's going to work. It's fine. It would probably even work in a server class machine for a while. But maybe after 6 months or a year or 16 months, all of a sudden it fails when the server class one maybe wouldn't have. Something like that. All right, so it's kind of planning for the future. And do you look at having one thing that's extra good, or do you start having duplicates? Kind of the jumbo jet model. What the 747 can fly on one engine, right? But they have 4 of them. If you lose one, you don't want that to be the end. If you lose 2, you don't want that to be the end. You start losing 2 engines, you're getting concerned. Actually, I'd be concerned losing 1 engine, right? Even if you have 3 backups. I don't want to lose any engines. When you're 50,000 feet up there, you don't want to lose engines. But in any case, that's kind of an idea of redundancy. They already have the best quality engines on there, and that's the biggest one they can get to fit on that wing. So, look, we got 300 people. We got them 50,000 feet up in the air. Let's put some extra engines on here to, just in case. Right? We'll use all of them at kind of a moderate speed, right? So we're not overly stressing any individual one. So those planes, how many of you have been on one of the big jumbo jets, like a 747? Well, most of you who've come overseas have been on one, right? Okay, yeah. Any of the big planes, right? Ones with gigantic engines. It always interests me when you're taking off and it feels like you're not moving, right? When I was when I was a little kid, I was first on one of these big jumbo jets, and it feels like you're in a movie theater, right? This giant thing, and you're like, this isn't getting off the ground. There's just no way this is getting off the ground. And this thing starts lumbering down the runway, and it starts taking off, and it's all like in slow motion, right? You barely feel like you're moving, and you're just waiting to slide backward out of the sky. Now, how many of you have flown in one of those smaller kind of like regional jets? You know, maybe you have 15 seats or something like that in them. They're fun, aren't they? I mean, you know you're going fast in those. Those things, they take off, and they're zipping all over the place. I was once on a flight coming out of Milwaukee to...
Not fun at all when the seat just like that.
Yeah, that's every seat when you're my size, fan. How many of you have ever flown Southwest? Like Southwest? You like competing for seats?
Yeah.
I love Southwest. You know why?
Free seat.
Southwest gives fat people free seats. So I get an extra seat for free, and I get to get on with the handicapped people.
Nice.
So I'm sitting there chilling while everybody else is fighting for seats. Okay. Oh, it's awesome. One time I was flying Southwest, I think to Orlando or something, and or Fort Lauderdale probably, and the flight was way overbooked, and they would have given me my extra seat. They'll kick people off for it. It's their policy. They have the official policy called passengers of size. You can look it up. It's legit. They gave me... Now, first of all, wouldn't you agree that an airline does not have to give fat people an extra seat? Now, that's something that I'm very impressed with, that they do that. The guy at the gate said, look, you know, we're really overbooked here, and we'll give you the seat, but, you know, you notice my wife, I have a pocket wife. So my wife is little. My wife's 5'4", 120 pounds or something. She's small. So her and I take up 2 seats total. I take up a seat and a half. She takes up half a seat. So he kind of recognized that, okay, they probably could squeeze into 2 seats if they had to. They gave me $100. They still let me pre-board, so I could just pick my perfect seat. But I didn't get the extra seat. They gave me $100 for my trouble. Isn't that awesome?
That's awesome.
Oh, and they gave me free drinks for the whole flight.
No, that's awesome.
Okay. Well, so anyways, I was telling you another story earlier about the smaller planes. So one time we were flying from Milwaukee to Chicago. And it's a real short flight, but they planned the flight as a 45-minute flight. You know, it was gate to gate, 45 minutes flight. And the plane was running late because they couldn't get the door shut. Something like that.
That is strong.
And I timed it. So I mean, we left late, and we had a flight to catch. And I think almost everybody on that plane was catching the same flight. So, and the pilot knew. You know, there was probably 18 of us on the plane, or 17. You know, not a whole lot of people. He took off. We never got above 2,000 feet off the ground. And you know, when planes take off, you know, eventually they kind of throttle back. No. Okay, he gunned it. We took off. Never got more than 2,000 feet off the ground. We were just like over the lake. We were in the air for 7 minutes. It landed in Chicago. We were early. Our flight left almost an hour late, and we arrived early.
7 minutes?
It was odd. It was one of my favorite flights. I mean, he took off so fast. It was awesome. I mean, you do the math. It's only like 92 miles or something like that. Planes can go 500 miles an hour. You know, and he didn't have that time of getting high and going back low. He just stayed low. But I like those little planes because you could really feel them, right? You feel all the little movements. I especially like when it's like really windy outside and they're making like major corrections during landing, and they're like 3 feet off the ground and they're like making these huge swings. Love that. Oh yeah. No, I am an official crazy person. My wife had never flown until she met me, and she thought that it was originally a smart idea to look at me, and if I was nervous, then she knew something was wrong. But I'm like the guy who hopes for horrible turbulence. But I think it's fun.
It's not fun at all. One time when I fly with the Unitas airline, the window doors just barely the wind is close to my face. The window doors just like
Yes.
closed, and
Yeah, it's fine.
And I feel like, if the wing is so much, it's gonna be took it off.
Yeah, rip the door off or rip the wing off.
Yes.
Both?
No, they're gonna rip the wing off and the
Oh.
window off. Well, it's not the wing, it's not the window.
That's
They
fine.
have a small, you can basically just like punch it, broke.
So, the it would be very difficult for a window on a plane to get broken. They're bulletproof. There's a bunch of panes in there. You couldn't shoot through the window of it. Yeah, planes are kind of amazing. But yeah, I'm all about the. We had an aborted takeoff once. That was in Atlanta. Yeah, somewhere in the training manual they broke all sorts of rules, I think. So we started taking off. We must have been 2 seconds from actually lifting off the ground, and all of a sudden it just cranks back. The front of it slams down. We pull off into the grass. And this is a big plane. Not an over the seas one, but across the United States plane. And then they say, we got a light coming over the thing. We're just check it out real quick. Just sitting in the grass, checking it. And other planes are still taking off. So finally, he pulls back onto the runway, and they're telling us that we need to don't use your electronic devices. I guess that must have been something like that. So we start taking off again, and right around the exact same time when we aborted the previous time, somebody comes over the intercom screaming, like, cell phones off, cell phones off. But we still took off. It's like everybody's super nervous, like are we gonna stay up? It was uneventful from there, but
So it's up.
yeah, I don't know what happened, but they were panicking. That it seems like somewhere in their manual they must say, don't go over the intercom in a panicky voice. Right. So another time we were in Arizona, and it was really bad fog. And we had been descending for landing for, it seemed like forever. And we just kept going down, down, down. And then all of a sudden we're right on top of houses. And we are nowhere near the airport. So he cranks it and pulls it up straight. You knew this wasn't where he wanted to be. And then, 20 minutes later we landed, but that was exciting. Loved that. And hey, we probably would have survived that. We would have crashed into some houses. People got hurt, but we must have been, 100 feet off the ground. We were low. we were low. So, how do we get into that? Dependability versus redundancy. Extra engines. All right, so these are all decisions. These are all, kind of ideas that we want to kind of keep in mind when we're talking about computer architecture, computer infrastructure, hardware, things like that. These are, it's not always about what's the fastest, or it's not always about what's the most reliable. There's some sort of combination in there depending on the application that we're applying this to. A lot of times for mobile, it's what's going to give us the best battery life balance between that and performance. You might be able to get the best performance if you're willing to have 30 seconds of battery life. I have another laptop that I use for the a lot of the virtual reality programming stuff, and actually I'll probably be using it in this class too when we start doing some of the assembly language programming stuff. But it's a bigger laptop than this. It's a PC, and it has a GTX 1070 graphics card. It's a high-powered laptop. Well, this is a really nice laptop. This is a more expensive laptop than that one. Well, this one I get 6 hours of battery life using it normally. That one I get about 1 hour of battery life if I'm using it normally. That one's geared more towards maximum performance, and this is more of a balanced experience. You decide which is the right tool for the job, right? Okay. All right, so let's start talking about, actually, I'm going to... I want to do this first. All right. Yeah, let's do this first. I'm just trying to time it right for the order of things we're going to do. Okay. So I told you about this earlier. We are going to talk about. I just want to talk about it a little bit earlier so we could segue into the Android application stuff after our next break, just for time. Okay, so how many of you are familiar with? We all watch TV, to some extent, right? So how many of you watched standard definition TV a while ago, right? Any of you still watch standard definition TV today? You have like one of the tubes in your house? Things are fuzzy. You can't tell whether it's grass or static. All right, so standard definition TV, which actually isn't even represented on here. It's called 480p. It's a 620 by 480 resolution. Not very high resolution. And it's actually not really compelling for us anymore because most of you have never even looked at it, right? You know, we've grown up in a time period, probably when you were kids, there was standard definition TV. But for the most part, for a long time, we viewed high definition stuff, right? And what's really funny is in the early days, we're seeing the same thing right now, is when people had standard definition TVs, and then all of a sudden HD came out. We talk about the data size of these things. People are like, well, do we really need HD? Because what you have is fine. And the fact that we had color was good. Well, then you finally saw your first HD show. Now, in the early days, the issue was that you had this technology that could show HD, show 1080p resolution, but you didn't have very much content that was 1080p resolution. But when you finally saw one, it really kind of hit sports first. So the first time you saw like a soccer game or something like that, you can actually see the sweat on them. You kind of recognize like how much better it was than standard definition, right? So most of us are used to high definition now, right? How many of you could go back and watch standard definition TV now? Or would you probably just pull out a book or watch YouTube on your phone or something like that? If you're at a place, let's say you go into a hotel and they have a standard definition TV in there, would you even waste your time? You'd have to be desperate, right? And it's just unacceptable. It's not TV. It doesn't meet our expectations because now everything's HD, right? And there's different levels of HD, but we'll talk about what that means. Now, what about 4K? Any of you have a 4K TV?
I have 4K monitor.
Okay, no 4K TV. Man, Van, you're starting to lose this war. I got 2 of them. I got a 60-inch 4K TV in my bathroom. I don't. But that's the only thing I would compete with is 128 gigs of RAM. I do have 2 4K TVs, but they're in the bedroom and the living room. Yeah, I just installed one under my couch, just in case if I'm cleaning.
60-inch TV was not 4K.
Yeah. So now we have 4K TVs. Okay, so let's go down that path. Why didn't you have a 4K?
Because I just bought the TV.
You just got the nice TV, right?
Yeah.
You got their nice high definition TV, and it's nice. You like it. And there really isn't enough 4K stuff out there to make it worth it, right? You'll get a 4K one as soon as there's so much stuff that's in 4K that you feel like you're missing out. Right now, you're missing out on like 3 things, right? You're not missing out on that much. So you can decide, am I going to be an early adopter? And am I going to pay a huge premium? 4Ks have come down quite a bit, so you're not really paying such a high premium now. Like if you were buying a new TV today, you'd probably buy a 4K, unless you were really, really trying to keep it cheap, because you get some pretty bad 1080p TVs. But really, you would just buy a 4K today because they're not that expensive. But really, you're kind of buying for the future, not really what you can get today. And that's becoming less and less true, like Netflix streams 4K and things like that now. But the punchline is we have a pretty similar type of like history repeating itself. When HD first came out, you had people who didn't want to jump ship on standard definition to go to HD because it wasn't worth it. Why should I pay this huge premium when there isn't really shows that are in that format? All right, so that's more the consumer model side of things. But what we care about more is data size for us. Okay, so we want to think more about like what's actually happening So if we think about more of a networking perspective on things, let's take Netflix for an example. So right now, Netflix has a 4K stream. All right, so we're going to look at a worst case. So I have 4K Netflix at my house, and so I have a 4K TV, and I subscribe to Netflix's 4K, and they actually have a whole bunch of shows that are in 4K. Pretty much every Netflix original that comes out is done in 4K. So if you are a Netflix junkie, 4K makes sense. If you get a smart TV that can do the streaming, but that's really the only source of your content is that type of thing. Okay, but notice here the resolution. So let's just operate off of the worst case scenario. So 4K is the highest resolution video stream we could have today. That's like in the realm of possible. It's not real common, but it's in the realm of possible. So that's 3840 by 2160. 3840 by 2160. What does that mean? When I say something has a resolution of 3840 by 2160, what am I talking about? Number of pixels. All right, so how many pixels is this? This is 3840 times 2160. It's 8.3 million pixels. So 8,294,000. Will that copy? Big money, big money. Pixels for a 4K screen. Now, talking about data size. Remind me, what's a pixel? We use this term very comfortably here. What is a pixel?
Single program.
Okay, don't overthink it. It's a little dot of light, right?
Okay.
Yeah. Nobody's kind of mentioned earlier that we have fancy names for things that mean easy stuff. Yeah, it's a dot of light, a dot of color. Okay? So what's more important for us is how do we represent a pixel? Typically, pixels are represented as how many bits? Because now we're back to this idea of bits, right? So is a pixel a single bit, just a 0 or a 1? How many colors could we show if a pixel was just a 0 or a 1? 2. Black and white. Is that what our TVs look like today? No. So more than 2 pixels, or more than 1 bit. You think 16-bit? How many of you heard of RGB? What's RGB? Red, green, blue. It's a color format thing. So what's the range of RGB? 0 to 255. 256 unique values, 0 to 255. So we have 0 to 255. So we have red is 0 to 255. We have green, which is 0 to 255. And we have blue, which is 0 to 255. And there's a couple of other models for color management stuff, but let's just use RGB as our example here. All right, so I need to hold 256 unique numbers. Now, do I need to hold, so we need to think about what size value, what's the smallest amount of memory that I would need to hold the values between 0 and 255? 8 bits. All right. So let's think about that. Let's think about what it means for something to be 8 bits. So the smallest 8-bit number is 1, 2, 3, 4, 5, 6, 7, 8. Largest 8-bit number is 1, 2, 3, 4, 5, 6, 7, 8. What's the value of this guy? That's 0. What's the value of this guy? You're the one who said 8 bits. Why? It should be 255. But let's figure out why it's 255. All right? It is 255. Now, I'm going to put some spacing in here. Actually, I'm going to... Actually, well, can I tab? Will it tab? Let me tab. Killing me. All right, so that is 2, 3, 4, 5, 6, 7, 8. Notice we have a little extra gap in here, but let's just call it good. Okay, I'm going to put this guy right here. This is the zeros place, or rather the ones place, twos place, fours place, eights place, 16s place, 32s place, 64s place, and 128s place. We could also think of this as 2 to the 0th place, 2 to the 1s place. Let me take a couple of spaces out here just to line this stuff back up. Yeah, so this is 2 to the 0th power, 2 to the 1s power, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7. Right? Okay, that's an important pattern because we're going to see when we move between other bases. It's going to be an important part of your homework assignment that we're going to start after our next break. Okay, so how do we figure out that this guy is 255? Well, what we do is we do 1 times 1. So we start with the bottom number here, multiply it by the top number. So this is 1 times 1 plus 2 times 1 plus 4 times 1 plus 8 times 1 plus 16 times 1 plus 32 times 1 plus 64 times 1 plus 128 times 1. We add all that together, we get 255. See how that works? All right, so now you said 8 bits to hold a value between 0 and 255. Now, we needed to look, because at this point we're looking at how can we represent, in memory, how can we represent the range of values, the 256 unique values between 0 and 255. Well, do we need to hold any negative numbers? Are there any negative numbers in there? We don't need to hold -1 or -2 or -3. So we can use all 8 of those bits for the whole value. We don't need anything for the sign, right? So 8 bits will get us all the values. We can use 8 bits, exactly 8 bits, to represent all of the values between 0 and 255. So we have 8 zeros is the 0, we have 8 ones is the 255, and then everything in the middle is some combination of zeros and ones, right? Well, I need red, green, and blue. So we need 24 total bits to represent the color of 1 pixel. Make sense? All right, so that's 24 bits. So here's my number of pixels, and each of those pixels requires 24 bits. I'm going to steal this guy here. Oh, come on. You can do it. Number of pixels times 24, that's the total number of bits. Okay. Now, sometimes it's a little hard for us to think about things in terms of bits, right? So let's bring this back into some something that's a little bit more palatable for us. So let's start off. Let's divide it by 8. That gets us bytes, right? divided by 1024 gets us kilobytes. Divided by 1024 gets us megabytes. Okay, so we have 23.7 megabytes. Megabytes for a single 4K picture to hold each of those pixels in 24 bits RGB color. Make sense? Now, when you're watching a TV show, do you see just one picture at a time? No. Now, when you bought your TV, Van, so you must have got a pretty nice HD TV. So 240 hertz or 120 hertz.
I think 240.
Yeah. So typically, a lower end HD TV would be a 60 hertz TV. Same thing when you think about monitors, computer monitors. Your common computer monitor is 60 hertz. Okay. Kind of your better gaming ones are 120 hertz or 240 hertz. What's a hertz? Yeah, so it translates into frames per second. So how many frames every second can that monitor show? Then we have to consider how many frames per second can the eye see? Terminator eyes can see 60 or 70, not human eyes. Okay, human eye can see, just to keep the numbers easy, let's say about 40 frames a second. Some people can see a little bit more than that. Some people can see a little less. Now, having said that, why then do we have monitors that can do 120 or 240 frames a second if our eyes can only see 40? Why does Van have 128 gigs of RAM? Right? So is it a waste of time? Waste of money? How many of you like watching sports on TV? Nobody? Nobody raises their hand? You're a cricket fan, right? Hey, you're not tennis. What sport are you watching if you're not watching tennis?
I like watching.
Yeah, I don't. What, you didn't even know, what sport do you watch? You watch NFL?
Football.
Football? All right, Packers fan?
Chiefs
Who?
fan.
Chiefs? Well, okay, well, I think worries there.
Yeah.
I don't necessarily care. I didn't even follow the NFL until I moved here, and then they wouldn't give me a driver's license until I pledged my allegiance to the Packers. So I either want the Packers to win or I want them to lose embarrassingly so I can people watch.
Yeah. Oh, that's the best.
I know.
That's awesome.
The worst thing would be to be a Bears fan when they lost to the Packers after Aaron Rodgers was hurt. How bad do you have to be? Yeah, it was bad. So, in any case, when you're watching sports, a lot of times when you're buying a TV at Best Buy, they're saying, oh, well, if you're a sports fan, you play a lot of video games, you want the 120 hertz, you want the 240 hertz. They're a lot more expensive, but that's what you want because it'll look better. So even though a human can only see 40 frames a second-ish, we can perceive the difference between 60 frames and 120 frames. There's kind of a perception of smoothness. Okay? Sometimes what you'll have if you're watching football, and you're watching on a lower end screen, sometimes you'll see almost kind of a shadowing of the ball when you throw it, or you're seeing somebody run down the field. It's not like major, but you kind of notice something, right? Like you see the ball kind of 3 or 4 times, but just barely the other 3 times. So that's kind of what's happening with the hertz. If you had 120 or 240 hertz thing, even if the signal was less than that, it's showing the frames so fast that you wouldn't perceive that. Make sense? So that's where the faster monitor can come into play. Same thing goes into the gaming industry. If you kind of go back to GPUs for a second, if you're playing a video game and you can get the $1,000 graphics card that allows you to play the game at 200 frames a second, which the human eye can't see. Okay? Or you can get the $300 graphics card that allows you to play the game at 200 frames a second. Actually, I gave 200 frames a second the first one. Lets you play the game at 60 frames a second. Still better than the human eye can see. Why would you spend the $1,000 for the much better graphics card if the lower one can keep up with the human eye? It's not the average case. It's the worst case. So people who play video games, you might have 90% of the time. Excuse me. You might have 90% of the time where you're getting 60 frames a second with the cheaper card, no problem. And you're getting 200 frames a second with the better card, no problem. As long as you're on a good enough monitor, they're going to look the same. Now, you get into a really, really busy city or something in the game. That 200 frames a second drops down to 100 frames a second. The 60 frames a second drops down to 11 frames a second. You'll notice the 11 frames a second because now you're dealing with a flip book. Or it's a still frame pictures. So people who are diehard gamers, they get the expensive hardware, not for the average case. It's for the worst case. When they run into an area that requires a lot of graphical processing, their worst case is better than the human eye or their monitor can show. So they don't notice any drop off. Okay? But in any case here, we're kind of going back to the idea of streaming Netflix. So we have 23.7 megabytes for one picture. Now, if we're going to stream at 60 frames a second, let's say to maximize on our mediocre quality TVs, and 60 frames a second clears what the human eye can see, and not all shows are at 60, but let's just use that as our number. Okay, so if we did this at 60 FPS, that translates into that many. So we'll do 0.8. That's megabytes per second. Right? That's over a gigabyte per second for 4K streaming. Yeah, we'll talk about that. We'll and we're not going to get into the nitty-gritty details of it, but just in general. All right. So this is megabytes per second, or if we want to divide that by 1024, it's 1.39 gigabytes per second. Make sense? Now, how long is your average TV show? 43 minutes? The hour-long shows, when you cut out the commercials, are like 43-minute shows. Okay, how many seconds is 43 minutes? So we have 43 times 60, 2,580. So let's just do this. Times, let's just do it again. Times 1.39 so that's gigabytes per show for 43 minutes. So 3,586.2 gigabytes for a 43-minute show. Now we need to go back and find out how fast does their internet connection need to be to maintain that. All right, so I need to be able to move 3,500 gigabytes in 43 minutes. I need to be able to move 1.39 gigabytes every second. Not gigabit. Remember earlier we were bragging about AT&T has gigabit internet, okay, which is 1/8 of a gigabyte internet. But I need to do 1.39 of those. So 1.39 times 8 is the number of gigabits I need. 11.12 gigabits times 1,024. So I need 11,386 megabit per second internet. Just hop on down to Spectrum. Say, look, I know you only offer 300 megabits. I need 11,000 and some change megabits. At that point, you might as well just say megs, right? I need 11,000 megs. You need really fast internet in order to do this, right? Now, I'm telling you, I have, hold on, I have 300. So my internet is 38 times too slow. I have the fastest that Spectrum has. But I'm streaming at 4K. And I'm not using my whole internet connection to do that. So what is Netflix doing? A lot of compression. So when you think about all those zeros and ones, you know, we're dealing with what's called raw video here, right? We're thinking about every single little individual pixel that's making up that 4K screen for each of the 24 bits of color for that pixel. So they're doing some pretty fantastic compression, and that's Netflix's magic sauce. It's that compression. All right? But the important lesson for us here is, do we kind of have a feeling for kind of sizes of data, how things are moving back and forth between stuff like that? Okay. So we want to get really comfortable with that. So what we're going to do here is let's take a break. Let's only do 10 minutes if we can, because I want to be able to get in and give you enough of a starting point for your app. Okay? So come back at 5 after, and then we'll start looking at the Android application that we're going to be working on.